The principle of a potential divider. Now I would like to introduce to you the principle of the potential divider because we will be using this very principle when we are dealing with potentiometers. Right before us we are having a circuit diagram, and this circuit diagram has a source of EMF, which is a cell, and it is connected to a slide wire AB. Now this slide wire AB has its length L, and we are going to get ourselves also interested in a portion of that slide wire which we have called AP, and that portion of that slide wire we are calling it length X. Now let's go on and find the potential difference across this slide wire. Now the potential difference, definitely this is a circuit now, the potential difference across this slide wire. So the potential difference across that slide wire VAB is definitely going to be given by V is equal to the current that is going through that slide wire times the resistance of that very slide wire. The same will be if we want to find the potential difference across the portion of that slide wire AP. It means that it's going to be still V, which is the potential difference across that portion of AP, is going to be equal to the current that is going through that portion times the resistance from A to P. Now speaking of the resistance of this slide wire, we are going to use our formula for resistivity. We all know that resistance can be expressed as the resistivity of this wire divided by the length of the wire over cross-sectional area. A is the cross-sectional area, L is the length of the wire, and this is the resistivity of the wire. If we are to use this value of this resistivity to substitute it right there, this is how things will turn out to be. That if we are to get the potential difference across wire AB, it's going to be equal to the current that is going through that wire times the resistance of AB. But now the resistance of AB can be expressed in terms of the resistivity of that wire AB times the length, which is the value of L, over the cross-sectional area A of that wire. So if we come and substitute this thing right there in RAB, we substitute it there, our VAB is going to turn out to be like this. VAB is equal to I, which is that current, times RAB. RAB is this expression we got, which is that right there. So we are going to get the same thing and get the potential difference across AP, which is right here. PD across AP is going to be equal to current going through AP times the resistance of that portion of the wire AP. Again, we know that RAP is equal to the resistivity of this same wire times X over A. Now X is the length of that portion of the wire times the cross-sectional area of that wire, which is the same as before. We are dealing with the same wire. So it means that therefore the voltage or the potential difference across that portion of the wire AP is going to be the current times RAP being that expression that we are substituting there, that constitutes our second equation. So what is going to happen here now? We want to compare the potential difference across AB and the potential difference across AP. When we compare them, it means we are just going to divide this, divide by that, these two equations. We shall divide them and we will end up with our expression. So when we divide VAP is equal to I times that, divide that by VAB is equal to I times resistivity times L over A. When we divide those two, you will find that the current is the same. It's the same amount of current that is produced by this. So it means I and I are the same, so they will cancel out. We are dealing with the same wire, so it has the same resistivity. So it means this two will also cancel out with that. And then this will become VAP over the potential difference across AB is equal to X over A, divide that by L over A. Of course, this is going to end up being V AP over VAB, giving us X over A times the reciprocal of this being A over L. This A and that A will cancel. VAP will over VAB is going to be equal to, this will be giving us X over L. This is X over L. Now, if we are interested in finding the potential difference across the portion of this wire, which so happens to be VAP, that means we shall make VAP the subject of the formula. VAP is going to be equal to X over L, multiply that by VAB. Now, if you look at this expression, we find that X is the small portion, divide that by the length of the whole wire. So meaning that this X over L in essence is trying to represent the fraction of that, of the X, this AP is the fraction of the whole wire. So it is the fraction of the wire we are talking about, multiply that by the potential difference across the entire wire, which so happens to be the EMF of that wire, VAB. So this expression shows us that the potential difference across a section of a wire is always proportional to the length of that wire. In other words, if the potential difference across this whole wire is 10 volts and this wire is 10 centimeters, it would mean that each centimeter of that wire is 1 volt. That's what we mean by saying that the potential difference across the section of the wire is directly proportional to the length of the wire. This also simply means that the longer the wire, the higher the potential difference across the portion of the wire that we have chosen. Now, this principle is what we are calling the principle of the potential divider, and this principle of the potential divider is exactly what we shall be employing when we are dealing with potentiometer circuits. A potentiometer is essentially a voltage divider that is used for measuring voltage potential, and it uses the principle of the potential divider. It has a driver cell, as we can see, and this driver cell is connected to a slide wire in a circuit we shall call the primary circuit. Now, this lower portion of the circuit is what we are calling the secondary circuit, and the secondary circuit is this lower bit, and it essentially always has the galvanometer plus something else connected here. Now, that something else can either be a cell or a resistor. Now, this driver cell, when it provides current, it's supposed to provide a constant amount of current that is supposed to be going through that potentiometer. Now, a potentiometer, how it works is simple. In case we want to find the EMF of this cell and we do not know the EMF, we are going to get this primary circuit, then we shall connect, like you're seeing in green, we shall connect this EMF to the secondary circuit with a galvanometer in series with it. Then what happens is that we are going to get this portion, or this sliding jockey, and we are going to slide this wire along the slide wire. We slide this portion along the slide wire. Now, as we are sliding this wire along this length, this galvanometer will be deflecting. Now, we are supposed to stop at a point whereby the galvanometer shows no deflection. When the galvanometer shows no deflection, it means no current is flowing through, and it means that at that point there is no current flowing through the secondary circuit. When there is no current flowing through the secondary circuit, it means that we have achieved what we call the balance point. And if we have achieved the balance point, then it means that we have what we call a balance length. So when we have a balance point and a balance length, the balance point being the point where the galvanometer shows no deflection, then we can go ahead and find the EMF of this cell using this potentiometer circuit. So now, how do we find the EMF of this circuit when we have achieved the balance point? Now, that is where the principle of the potential divider comes in. Now, in our previous explanation, we said that we derived the principle of the potential divider and discovered that the potential difference across a section of the wire, like for example the portion of the wire AB, in which case the point B being the balance point. So the potential difference across this portion of the wire is always directly proportional to the length of that wire, and that is the principle of the potential divider, and that's the principle we're going to use here. So when this balance point is achieved, the potential difference again between A and B, the balance point, this being the balance length, is going to be equal to the potential difference across whatever is in the secondary circuit. If you're having a pair of resistors, if you're having the EMF, or cells, the potential difference across AB at balance point is going to be equal to the potential difference across what is in the secondary circuit. Now in this case, since we are interested in finding the EMF of this cell E, it means that when we achieve balance point, the potential difference across that portion of the wire AB is going to be equal to the potential difference across that cell. In this case, which we are saying that VAB is going to be equal to E. But we know that the potential difference across AB, which is a portion of this whole wire, is going to be equal to, now from the principle of the potential divider, we said that the potential difference across a portion of the wire is directly proportional to the length of that wire. So if this length, the length of this wire, of the balance length, if we call this balance length to be our value of X, and the length of this whole wire from here to right to there is L. So it would mean that the PD across AB over the PD across AC is going to be equal to the length AB over the length AC. And this is what we did here, that the PD across AB divided by the PD across AC is going to be equal to the length X over L, over the original length. So we derived this, we got this from our previous video, the principle of the potential divider. So we go ahead and say, so meaning that if this is how we can, the other way we can express the potential difference across AB, it means that our EMF E is going to be equal to the PD across AB, which is expressed in terms of this, which is that right there. So we can go ahead and find the PD across E. So this V, we have V over L right there. So we have the potential difference across SC over L, which we rearranged here as VSC over L times this X. Now this VSC, this is the potential difference across the entire wire. Divide that by the length of the entire wire. Gives us what we call the PD per unit length of the wire. Now since we know that the potential difference across a wire is directly proportional to its length, which simply means that the longer the wire, the longer the potential difference, and the shorter the wire, the less the potential difference. It means that this potential difference and the length of the wire have a linear relationship. So if we divide the potential difference of the whole wire by its length, it means we are able to get a constant called the PD per unit length. So it means that here, since we are saying that when we obtain balance point, that the potential difference across the balance length is going to be equal to the potential difference across whatever we have here in the secondary circuit. For us to easily get this potential difference, we simply have to get the balance length, and then we multiply that balance length, which is in this case X, we multiply it by the PD per unit length. Now the PD per unit length is what is being represented by VSC over L, which we are calling a constant K. So for us to get the EMF E is we get the PD per unit length, which is the value of K, times the balance length we've gotten. Now, the potentiometers can have a slide wire of any length. It can be 1 meter, it can be more than 1 meter, depending on the needs. So what we need to find is the potential difference across the entire length of the wire. Divide that by the entire length of the wire to get the value of K. This value of K is what we are calling the PD per unit length of the wire, and the process of obtaining this value of K is what we call standardizing the potentiometer, or the process of standardization of a potentiometer is in essence the process whereby we seek to find the PD per unit length, because once we know the PD per unit length of any slide wire, then it makes work easy for us to be able to get the potential difference across whatever components that are in the circuit, whatever components that are in the secondary circuit. How to standardize a potentiometer? Now, standardizing a potentiometer is simply the process of obtaining the PD per unit length of a potentiometer wire. How we do this is simply put, looking at this experiment, this is how we set up the experiment. After setting up the experiment, as we have, this is a potentiometer definitely with a slide wire of uniform resistance. Then we have a driver cell right there and a switch together with a galvanometer connected in series with a cell whose EMF is known. That's why we call it a standard cell. This is a standard cell, and by definition a standard cell is a cell whose EMF is known. So the first step here is that a standard cell, which is in this case E0, and a driver cell, which is right there, are connected in the potentiometer as shown. After connecting this in the potentiometer, we close switch K, and after closing switch K, we shall get this jockey and we shall slide it along this potentiometer wire until the point where there is no deflection of the galvanometer. When we reach a point where the galvanometer shows no deflection, then that means that is the balance point, and then we shall stop at that. When we attain that balance point, then we will go ahead and measure the balance length. In this case, we are assuming that our balance length will be L0. So we shall read it off and record it. After measuring our balance length, then we'll go ahead and find the PD per unit length. Now, of course, when we get the balance point, we are aware that when the balance point is achieved, the potential difference across the portion of the wire, that is the portion between point A and that balance point, is equal to the potential difference across the EMF. So this is what we are doing here, that the potential difference across the balance length is equal to the potential difference across the standard cell E0. And we know that the potential difference across the balance length is going to be the PD per unit length, which we are calling K times L0, is equal to E0. E0 being the PD across the standard cell. Now we know the standard cell, we know its EMF, that's why it's being called the standard cell. And so we simply find the value of K by making it the subject of the formula, and we are able to get the value of K. Now the value of K in this case is going to be the PD per unit length of that slide wire. We'll do an example. So this question says that there are two cells A and B connected in series, and when they are connected in series, they give a balance length of 758 millimeters along a potentiometer wire. When cell B is removed, the balance length will fall to 123 millimeters, and now the question is asking us to find the PD per unit length and the EMF of cell B, and they are telling us that a condition that one of the cells that are being connected in series here, one of the cells there, its EMF is 1.5 volts. So with these kinds of questions, we first diagrammatically summarize it. In the first instance, which we've called case 1, two cells A and B are connected in series. So we are having here two cells A and B, and they are connected in series, and they give a balance length of 758 millimeters. So when we connect them in series, they give us a balance length of 758 millimeters along a potentiometer wire. When cell B is removed, so meaning when we remove this cell B and we only leave cell A, which the question claims is only having 1.5 volts, the balance length will fall to 123 millimeters. So this is the diagrammatic summary of this question. So let's go ahead and find the PD per unit length. Now, finding the PD per unit length, if you look at case 1 and case 2, this diagram can help us to find the PD per unit length, because at balance point we know that the potential difference across the slide wire there is equivalent to the potential difference across this cell. And since we are having this cell being 1.5 volts, it means that the PD per unit length can be got. To answer Roman 1, we shall say from the second case, let's call it case 2, we know that at balance point that the potential difference across this portion of the wire, which is the, let's call this AB. So in case 2, we know that the potential difference across AB, which is VAB, is going to be equal to the PD of A, which is going to give us the EMF of cell A, which is the EMF of cell A. And we know that the PD across that portion of the wire AB is given by the PD per unit length times the balance length. So the PD per unit length times the balance length is equal to the EMF of A. Now the PD per unit length, which is the value of K, which we are looking for, we shall remain as K. Multiply that by L. L is the PD per unit length, which is 123 millimeters. So it's going to be 123 millimeters is going to give us the EMF of cell A, which is 1.5 volts. So our value of K there is going to be 1.5 volts. Divide that by 123 millimeters. And definitely our answer right there is going to become 0.0122. These are volts per millimeter. And now this is our value of K, or call it the PD per unit length. Now these balance lengths have been given to us in millimeters, but sometimes they can be given in centimeters. So of course, if it was in centimeters, our units here would be volts per centimeter. If it was in meters, our units here would be volts per meter. So it's about the units will depend on the length, the units that were used in the measurements of length. So that is Roman 1. Our Roman 1 is PD per unit length. So now Roman 2, they want us to find the EMF of cell B. So if we look at our second diagram here, this one here, to find the EMF of cell B, still we are going to use the same principle that at balance point, the PD across this portion is going to be equal to the PD across whatever is in the secondary circuit. So in this case, if I may use Roman 2, we know that, let's call this X and Y. So the PD across X, Y is going to be equal to the PD across the combination here, the total EMF across the combination here of AB. And we know that the PD across this balance point is going to be given by the PD per unit length. Multiply that by the balance length is going to be equal to the EMF here. Since these two cells are in series, so it means that the total EMF here is going to be the EMF of A plus B. The EMF of A is 1.5 plus the EMF of B, which we are definitely looking for because they want us to find the EMF of cell B. So when we make K, we got K right here as, because we are dealing with the same, slide wire, so it means that the PD per unit length is the same. So it's going to be 0.0122. Multiply that by the length. Now the balance length here is 758 millimeters, is going to be equal to 1.5 plus the EMF of cell B. Now when we make EB the subject of the formula, we shall end up with 7.74 volts. In our previous video, we were exploring how we standardize a potentiometer, and we explicitly said that standardizing a potentiometer is the process of finding the PD per unit length of a potentiometer wire, or the PD per unit length of a potentiometer. When we find the PD per unit length of a potentiometer, we are able to just simply tell the potential difference across a portion of the wire by multiplying that length of that portion of that wire by the PD per unit length. So in this video, we are going to explore how we measure the potential difference of this resistor using a potentiometer wire. Now if you look at This potentiometer, of course, we have the driver cell, these two switches K1 and K2. K1, if we are to close that K1, it means that we are putting this driver cell to release current into the primary circuit, and then these two also. And then K2 also brings this other cell 2 into the circuit. So as we start the illustration of this experiment, it is under the assumption that we have finished standardizing our potentiometer. So after standardizing our potentiometer, and now we are aware of the PD per unit length of this potentiometer wire, we will go ahead and connect it as shown below. So after connecting our potentiometer circuit as shown, we shall close switch K1 and switch K2. And after closing these two switches, this galvanometer will deflect. So we shall move this sliding jockey along this potentiometer wire, and we shall stop at a point where this galvanometer shows no deflection. When the galvanometer shows no deflection, it means there is no current going through the galvanometer, and therefore there is no current going through the secondary circuit. So when the galvanometer is showing no deflection at that balance point, let's say the balance point is B, the potential difference across the portion of that wire AB will be equal to the potential difference across the components in the entire circuit. So here it means that when we get the potential difference across the portion of the slide wire that has between the point A and the balance point B, the potential difference across that portion will be equal to the potential difference across this resistor. Remember, here we are interested in finding the PD using the potentiometer, and in this case the PD we are interested in finding in this is this one. We want to find the potential difference across this cell. So after closing those switches K1 and K2, and then we slide this jockey and we obtain a point where there is no deflection, we will go ahead and write our calculation that the potential difference across the components in the secondary circuit, which include that resistor whose potential difference we are interested in finding, is equal to the potential difference across the balance length AB. And since this is already a potentiometer whose PD per unit length we know, K, it means that that potential difference we're looking for, V, is going to be equal to K times the balance length L, which so happens to be AB, or we can call it LAB. Now, of course, K is going to be equal to the value of K, like in our previous video, is the standard cell we used. Divide that by the balance length that is corresponding to the standard cell. Now, this is coming from our previous video when we were finding the value of K, which is the PD per unit length of the potentiometer wire. And this is definitely how we will always be finding the potential difference across the elements in the secondary circuit. It's a matter of finding the balance point. When the galvanometer is not deflecting, then we get the balance length. And after getting the balance length, the principle here is that the potential difference across the balance length is equal to the potential difference across whatever is in the secondary circuit. And then we proceed on and on with our calculations. Towards the end of this video, I'll be talking about the precautions that we need to observe when we are dealing with potentiometer circuits. But before we get into that, we'll be exploring how we compare two EMFs using a potentiometer circuit coming up. Now, when comparing two EMFs using a potentiometer, we can use this kind of circuit the way it is, the way I have drawn it. Now, the EMFs of two cells can be compared using a circuit where we have, of course, the driver cell right there. We have switch K1 right there. We have switch K2. We have, of course, this switch S. Of course, this is where we are going to be putting S, position 1, then position 2. When we put it on position 1, it means that we have rendered this lower part redundant, and it is only this cell that is in the circuit. When we put this switch S on position 2, it means that we have rendered this upper bit, this part of the circuit, redundant, and it's only this that is actively in the circuit. Now, E is a cell whose EMF is not known. E0 is a cell whose EMF is known. And this is what we are calling the standard cell. A standard cell is a cell whose EMF is known. We have right here a resistor we've called P. It is a protective resistor that we have connected in series with the galvanometer. and we connect this protective resistor in series with the galvanometer so that we protect this galvanometer from excessive current. Now, of course, the procedures of our experiment will reveal that we first obtain the balance point when the protective resistor is in the circuit. So when we get the balance point when the protective resistor is in the circuit, that balance point we will have achieved is just an approximate one. Then we will go ahead and get the accurate balance point by removing this protective resistor out of the circuit. We remove it out of the circuit by simply closing switch K2. Of course, when we close switch K2, it means that any current that is flowing through here will bypass this resistor like that into the galvanometer, and then we will obtain the balance point. And after obtaining the balance point, that balance point we will have obtained will be the accurate one, and that is what we will be taking. This protective resistor just protects this galvanometer from excessive current. So to begin with our experiment, first of all, we are going to close our switch K1, and we put this portion or this switch S to position 1. So after putting switch S to position 1 and switch K1, we slide our jockey, or we tap it along this wire until we obtain an approximate balance point. We call it an approximate balance point because this protective resistor now is in the circuit. So after getting our approximate balance point, that is when the galvanometer is not deflecting, we then close switch K2 so that we remove this protective resistor out of the circuit, and then again we slide this galvanometer, we slide this jockey along the wire until we get the accurate balance point. So when we get the accurate balance point, that is at the point when the galvanometer is not deflecting, we then go ahead and get the balance length, which we shall call L0, since it is corresponding to E0, the standard cell. And definitely we will go ahead and write our equation that at balance, that this EMF E0 is going to be equivalent to the potential difference across the balance length, and since that will be the balance length L0 times the PD per unit length. And this is what exactly we are talking about. When we first obtain the balance point, E0 is going to be equal to the PD per unit length times L0. That is our first equation, equation 1. So after getting our first equation, we are going to repeat the same procedure again. This time round, we shall get our switch S connected to position 2. When we connect it to position 2 with switch K2 open and switch K1 closed, we shall tap our jockey along this wire, and then we shall get an approximate balance point. Then thereafter, we shall close K2, and then we shall slide our wire along our jockey along this wire, and then we shall get the accurate balance point. Then we get the accurate balance point, we shall read and record the accurate balance length. Let's call it L. Then, of course, when we get our accurate balance point L, we know that the PD per unit length times that balance length is going to be equivalent to the EMF, or the potential difference across that cell. And so we will be able to compose or write our second equation in that right. So it will be that E, which is in the secondary circuit, is going to be equal to the PD per unit length times the balance length L, the accurate one. And of course, after getting our two equations, we compare them. We now have two equations. We have our first equation right there, and we have our second equation. So since this is about comparing two EMFs, so we shall get equation 2, divide that by equation 1, and we will get an expression that will enable us to compare the EMFs of the two cells. And this is exactly what has been done here. Equation 2 divided by equation 1 gives us E over E0 is equal to KL over KL. Now, since the PD per unit length is the same, because we're dealing with the same wire, it means these values of K will cancel out. Then we shall end up with an expression that E over E0 is going to be equal to L over L0. And from this expression, we are able to compare the EMF of the two cells. Now, of course, the EMF of E, the cell, is not known, but we know E0 is a standard one. So in case we wanted to find the EMF of this cell E, it's a matter of making this the subject of the formula, and we shall make this the subject of the formula like that E is going to be L over L0, multiply that by E. And there we're able to get the EMF of the unknown. First of all, when you connect your potentiometer circuit and you're currently not using the potentiometer and you're not taking any readings, it is always advisable that you always leave your switches open. You should only close your switches. For example, this kind of switch, you should only close them only and only when you are measuring or when you are actually using the potentiometer to measure something. Otherwise, if you're not using the potentiometer, you're not taking any readings, and you leave your switches closed, they'll be draining the cell, and when they drain the cell, you won't be able to get accurate results in the forthcoming readings or measurements you'll be making. So it's always advisable that you always open the switches when the measurements are not being taken to avoid draining the cell. Also, you need to ensure correct polarity of cells. That is, for example, you look at this driver cell and this driver cell, the positive terminal is always connected to the positive terminal in the secondary circuit at that point. That's the correct way to connect them. And the negative connects with the negative here from at the jockey right there. This is exactly how it has been done even with this diagram, that the positive polarities are connecting at point A and the negative polarities right there, they are connecting at point J. So you are supposed to ensure that the polarity is correct in terms of its connectivity. Otherwise, if you do not connect these polarities the correct way, you won't be able to obtain the correct balance point. Now, also the driver cell current should be the kind of current that should be able to maintain a constant amount of current for a long period of time, so that you're able to have a stability of results. Now again, the driver cell, still speaking about the driver cell should not be so big so as not to overheat the potentiometer wire. It is always advisable also to always put the protective galvanometer it is always advisable also to protect the galvanometer from excess current by putting a protective resistor in series with it. Now the potential difference of the driver cell should be greater than the potential difference of the cells in the secondary circuit. Otherwise, there won't be a balance point. This potential difference should be higher than this. And also, as you're trying to slide this jockey along the wire, avoid sliding this while the jockey is in contact with the wire, because you will end up scraping off part of this wire. And when you scrape off part of that wire, it means you're going to make this slide wire non-uniform. It is important that this wire is having a constant cross-sectional area all through to be able to get accurate results. If you keep sliding this jockey while it's in contact with this wire, it will end up scraping off some portions of this wire, and as a result, that will distort the uniformity of this slide wire. And when the uniformity of the slide wire is distorted, it means that the results you'll be getting won't be accurate, or the small EMFs, sometimes referred to as thermometric EMFs, of course thermometric EMFs are actually small EMFs, are always of the order 10 to the power negative 3 or 10 to the power negative 4 volts. They are always very small. Now we're going to discuss how we find these small EMFs using a potentiometer. Now in our diagram here we can see a potentiometer circuit. It is connected to a thermocouple, and of course it is from the thermocouple, the EMF of the thermocouple, which is always very small, is what we seek to establish using a potentiometer. Now since the EMF, or the potential difference that is to be measured across this thermocouple, is very small, it means that the current that is flowing through the slide wire should be equally small. Why should it be equally small? So that it's able to match up with this small thermometric EMF that we are able to, or that we seek to find. So we are able to achieve this by connecting a uniform slide wire in series with a very high variable resistances, and of course these very high variable resistances that we are connecting in series with the slide wire are meant to minimize the amount of current flowing through, so that when we are able to step down or to reduce the amount of current flowing through the primary circuit, we are able to get a potential difference across the slide wire that is of the same order as the potential, the EMF that we seek to establish or we seek to measure in the secondary circuit. So to begin with the description of the experiment, we set up the circuit as arranged below. Of course, in this circuit, you can see a driver cell right here. We have two cells that are two variable resistors right here, variable resistor M and variable resistor Q. This variable resistor is in series with that slide wire AB. Of course, the slide wire is having a slide jockey attached to it, which jockey is meant to hover all over it to be able to establish the balance point. This is connected to a galvanometer, a center zero galvanometer, which is also in series with a protective resistor that is meant to protect it from excess current. This has a bypass switch that bypasses the protective galvanometer. We normally do that when we are trying to get the actual balance point. Then we have switch S, which we shall connect to a port 2 or port 1. When we connect S to 1, it means we have killed this blue part of the circuit and it's only this green one that is working. If we connect this S to port 2, it means we've killed the green part and all the secondary circuit is only comprised of the blue one. Then we also have the standard cell. Of course, the standard cell is a cell whose EMF is known. So this is the setup of our apparatus. So this is the setup of the circuit. This is how we connect the circuit. So after setting up the circuit like this, the variable resistors Q and M are first adjusted so that the PD that is flowing through the primary circuit is very small. And of course, when it is very small, it makes the potential difference across the slide wire to be small too, so that it matches with the EMF, or it matches with the order of the EMF that is supposed to be measured in the secondary circuit. Remember, we said that for thermometric EMFs, these are very small EMFs whose order is times 10 to the power negative 3 volts or times 10 to the power negative 4 volts. They are normally really very small EMFs. So after doing that, our next procedure is that now we connect port S, we connect it to port 2. Of course, when we connect S to 2, it means that this green part of the circuit is eliminated. We are now concerned with this. So when we connect S to 2, we now start sliding this jockey along AB so that we obtain a balance point. We do so while K is open. So we slide the jockey along AB until we obtain a balance point where galvanometer shows no deflection. So when we get the balance point at that point J, we then go ahead and adjust these Q and M, the variable resistors. We adjust them again. The reason as to why we adjust them again is to make sure that we are getting a reasonable length, a reasonable balance length. So it is more like try and error. You keep adjusting Q, you adjust M, so that at balance point you are able to get a reasonable or a measurable balance length. So after getting a measurable balance length, then we bypass this protective resistor. So that means we're going to close K. So when you close K so that we bypass it, then we adjust this jockey again and we are able to establish the accurate balance point when we've put this in the circuit. So when we get the accurate balance point, remember we say that at balance point the potential difference across the portion of the balance point of the wire is equal to the P. Now here is equal to the potential difference across the components in the secondary circuit. Now in this case, since we connected S to 2 and this green part is not out, it's out of the circuit. When we connect S to 2, it means that the ES, which is the EMF of this standard cell, since the EMF of this standard cell is equal to the EMF between J and C. But remember, with J and C and J, we are having this portion of the wire, and then also along we have Q involved. So it means that in our calculations we're supposed to include Q as well. So in our write-up for the balance point, when S is at 2 and K is closed, at balance, this is how it will look like. So at balance, ES, which is our standard cell, the EMF across the standard cell is going to be equal to the potential difference that is across C and J. Of course, the potential difference across C and J is going to be the current that is going through that portion times the resistance between C and J. Now, unlike before where the balance, it was all through was just a wire, in this case, our effective resistance between C and J is comprising of a variable resistor Q and also that portion of the slide wire to the balance point. So it means that in this case, it's going to become I times the effective resistance is going to be the Q, which, since that variable resistor Q is in series with that portion of the balance length, so it's going to be that resistance, the effective resistance of that portion is going to be Q plus the resistance of the portion of the balance length. Of course, the resistance of the portion of the balance length is going to be the resistance per centimeter, multiply that by the balance length being LS. Now, how do we get resistance per centimeter? Remember, we said earlier, one of the factors that affect resistance of a conductor is distance. The longer the distance, the higher the resistance. In other words, the resistance of a conductor is always directly proportional to the length. So it means that if you're having a wire and it is, let's say, 10 centimeters, and you want and you know that it's the entire resistance of the wire is 10 ohms, for you to find the value of R, which is the resistance per centimeter, means you're going to divide the 10 ohms, divide that by the 10 centimeter, and so it means that it will be 1 ohm per centimeter. So that's how we get the resistance per centimeter. We get it by simply getting the resistance of the whole wire, and we divide it by the entire length of the wire to get the resistance per centimeter, or the resistance per unit length. So this is how we get our first equation, or our first expression. Again, where R is the resistance per unit length, the length can be centimeter, it can be in meters or in units, and L subscript S is the balance length. So this is what we get when we connect S to portion 2. Now we are going to repeat these procedures, but this time around we are going to connect S to portion 1, or to port 1. So when we connect S to port 1, it means that we have killed this blue part out. And so what is in the secondary circuit, the functioning is this, then from A like that. So this is what is working. So the EMF of the slide wire is now balanced against the thermometric EMF. And this is achieved by putting S into position 1. When we put S in position 1, while K is open, we are going to move the sliding jockey along AB and obtain an approximate balance point. After getting an approximate balance point, then we bypass the the protective resistor by closing switch K, and then we continue tapping the jockey along the length AB until we get the accurate balance point. So when we get the accurate balance point, we go ahead and measure the balance length we've gotten, which in this case we shall call it L, and then we'll go ahead and make our calculations. We shall go and say at balance there for E, the E I'm talking about is this, the EMF across the thermocouple, which is the thermometric EMF we are looking for, is equal to the potential difference across the balance point AJ. Of course, a point across A and that portion J. And of course, we know that this EMF here, E, is going to be equal to the current that is going through that portion times the resistance between A and J. And we know that that is going to be equal to current times the resistance across AJ is equal to the resistance per centimeter times the balance length we got, which is L. And there we'll be getting our second equation. So of course, now after getting our two equations, now we will go ahead and compare the two equations. Now our first equation was this, our second equation was right there. So we can go ahead and substitute the value. The current going through that portion of the wire is the same. So we can substitute for I in this second equation. Since we're interested in finding the thermometric EMF or the small EMF in the secondary circuit, we will go ahead and substitute for the value of I into this expression, and we're able to get our value of E. This is exactly what was achieved here. We got our value of E is equal to IRS. This is the second equation. So to substitute for value of I, we go and make I the subject of the formula in this equation. When we make I the subject of the formula in this equation, we have I is going to be ES over this, which is what we've done here. It's going to be ES over Q plus RLS. And of course, that is, we've just substituted for the value of I in this expression, times R, which is the resistance per centimeter, times LS, which is the balance length. Then of course we end up with our expression E is equal to this. We know the balance length LS, we know the resistance per centimeter, we know the value of Q, which is the variable resistor, we know the EMF of the standard cell. So since we know all these, then we can go ahead and find the EMF of the thermometric EMF or the small EMF that we seek to find. Now this is one way of doing it, or you can treat these two equations in this another way. You can choose to get equation 2 and you divide it by equation 1. Then when you divide these two equations, since you're looking for the value of E, you make E the subject of the formula and you'll come up with the same expression. This is the second equation. E is equal to IRLS. Divide that by the first equation, which is ES is equal to I into Q plus RLS. And of course from here, we can go ahead and make E the subject of the formula by simply saying E is going to be I R LS times ES. Divide that by what is down here, which is I into Q plus RLS. This value of I and that value of I will cancel out, and you remain with your expression for E being RLS ES and you'll find that this expression we've got here is exactly the same as this expression that we have arrived at there. And that is how we're able to get the thermometric EMF using a potentiometer. In this video, we get to discuss how we find the internal resistance of a cell using a potentiometer. This is Kisembo Academy. Now, this is how our setup will be like. Of course, our potentiometer, it's having a driver cell right there. With a certain switch we've called K1, this is connected to a slide wire AB. This is the primary circuit. So to it is connected the secondary circuit, which is comprising of the cell whose internal resistance we want. We call this is the cell, and now that, of course, this internal resistance small r is embedded inside the cell, but we'll represent it like that. So it is as though it is in series with the cell, but actually this internal resistance is inside that cell. So this is the cell whose internal resistance we want. Then we have a resistor whose resistance is variable. Then we have K2, K3, and then we have this protective resistor, which is meant to protect the galvanometer from excessive current. So there will be two major procedures here. The first major procedure is, first we are going to balance this cell whose internal resistance we know. We are going to first balance it against this slide wire, and we do that when this K2 is open. And then afterwards we shall close this K2 so that we bring it into the circuit, and then we adjust this rheostat to a suitable resistance, and we will be able to balance this whole apparatus or this whole combination against the slide wire, and we'll be able to get what we want. So let's get started with the experiment. So first of all, we are going to first balance this cell against the slide wire. We do that by first of all closing switch K. When we close switch K, of course it means that now this driver cell is going to start providing current. When we close switch K, that is while leaving K3 and K2 open, we move this slide jockey along the wire AB, and we tap it along the wire up to a point whereby the galvanometer shows no deflection. Now when we get that point where the galvanometer shows no deflection, that is the point that the balance length that will correspond to that point, or the point we will have gotten, will be just an approximate balance point. Why? Because when we connected this in the circuit, we have a protective resistor that is in series with the galvanometer. So when we get the approximate balance point, now we go ahead and get the actual balance point by closing off K3. Now when we close K3, in essence we are bypassing this protective resistor. So in essence, as current is, we'll bypass it when we close K3. When we close K3, we continue to tap this jockey along the slide wire AB until we're able to get the approximate or the accurate balance point. And when we get the accurate balance point, that is when K1 is closed and when K3 is also closed, while K2 is still open, we're able to get our first expression. And that expression is E is equal to KL naught. The EMF is equal to K, which is the PD per centimeter or the PD per unit length. Multiply that by the balance length we got. This balance length L naught is corresponding to the potential difference when we balance this cell, whose internal resistance we want, across the slide wire. So our next step now is to adjust. We now go ahead and adjust this variable resistor so that it attains a suitable value. And then after adjusting this rheostat until it gets a suitable value, we balance it against this slide wire. How do we do this? So with K1 and K2 closed, while K3 is still open, an approximate balance length is going to be obtained by sliding this jockey or by tapping it along the wire AB until you get a point whereby the galvanometer shows no deflection. So after getting that approximate balance length, that is when the galvanometer is not showing any deflection when K1 and K2 are closed, we go ahead and close K3. After closing K3, it means we've bypassed the protective resistor. So we go ahead and tap this jockey along the slide wire AB until we get the actual balance length. So when we get the actual balance length, we are able to get, we know that when we get the balance length, the potential difference across this resistor is going to be equal to the potential difference across the balance length we've got obtained. And so it means that PD across this resistor IR is going to be equal to the potential difference across the balance length, which so happens to be the PD per centimeter or the PD per unit length. Multiply that by the balance length, and in this case our balance length will be L. So this is what I was saying, that the potential difference across this resistor, now that we've connected it into the circuit, R, which is the current going through this, times R, which is the resistor here of this variable resistor, is going to be equal to the potential difference across the balance length, which so happens to be the PD per centimeter or the PD per unit length. Multiply that by the balance length that we got. So we have our second expression here. So now that we have now two equations, now we go ahead and find the internal resistance of the cell. So just like I've been describing, so we go ahead and repeat the experiment, using different values of R. It means we are going to keep adjusting this rheostat so that we get different values of R, and as a result we get corresponding values of L, the balance length. We go ahead and tabulate those results, but as we tabulate those results, we include in our tables of results the values of 1 over capital R, 1 over L, the balance length that is corresponding to R. So when we tabulate our results that are having values of 1 over capital R and then values of 1 over L, L being the corresponding balance length that we are getting, that is when we are able to find the internal resistance of the cell. Of course, when we draw our graph, the y-intercept, which so happens to be negative 1 over R, is where we are able to extract our internal resistance of the cell. So this intercept is the same as 1 over negative R. Of course, when we make R the subject of the formula, we are able to get our R being equal to negative 1 over the intercept. So now what is the theory behind this? How do we arrive to this? This is the theory behind the experiment. Remember from earlier, we first balanced the dry cell whose internal resistance we want against the slide wire, and when we did so, this is the expression we got. Then thereafter, we connected this variable resistor into the circuit by closing switch K, and when we connected this variable resistor into the circuit, into the secondary circuit, we balanced this combination against the slide wire, and we were able to get another expression. And that was the expression we got at balance. So these two expressions, the first one and the second one, are the ones that are going to be our basis to explain the theory that helps us to get the internal resistance of the cell. So these are our two equations. This is the first one, and that's the second one, like I had showed you earlier. So looking at this second equation, of course, IR is equal to K times L. Now remember, this is coming from the secondary circuit. In the secondary circuit is where we are having a cell whose internal resistance we want. And since we are having the internal resistance that we want, this value of I, which so happens to be the current, can be expressed in terms of this, from this formula. We've explored this formula in our previous examples. EMF of a cell is going to be equal to I times the effective resistance of the external circuit plus the internal resistance of the cell. Remember, the internal resistance of the cell is always in series with the external circuit. So when we make I the subject of the formula, in this case, this is the expression we get. When we get this expression for the value of I, we go ahead and substitute this expression in that portion I here. So this I is this, it's what we've done here. We've gotten this equation 2, and we've substituted for the value of I, as we've put E over R plus R in that value of I, times R, which is that R is going to be equal to K times L. And here we have our equation 3. So now we are going to deal with equation 3 and equation 1. And these two equations, we are going to divide them. When we divide those two equations, equation 1 by equation 3, E divided by that is going to be equal to, this is the portion of equation 1, and that is the equation 3. When we divide this, of course, E divided by this expression, this becomes multiplication sign when this becomes the reciprocal. So that's how it becomes E times the reciprocal of this, which is R plus R. Divide that by ER is going to be equal to this over that. Of course, from here, E and that, these two will cancel. Even this K and that K will cancel. You remain here with L naught over L. And here we have R plus R over capital R. So right there, disbanding this is the same as R over R plus small r over capital R is equal to L naught over L. That's the expression we have. Of course, this R and that R will cancel. You remain with 1 right there. So it becomes 1 plus R over capital R is equal to L naught over L, which is just this step. So we divide through by R so that we have 1 through. We divide through by small r. When we divide through by small r, this becomes 1 over R, like here, is equal to, of course, R over capital R here. The R's will cancel. Is going to be L naught over LR. That explains our next step. So this becomes 1 over small r plus 1 over capital R is equal to 1 over L times L naught over R. We simply separated this expression into 1 over L, and we put this expression on its own, L naught over R, like that. And definitely we will end up, when we push this to this side of the equation, it becomes minus 1 over R right there. So it becomes 1 over R is equal to that minus 1 over R. And when you look at this closely, it's in the form of y is equal to mx plus c, where our value of y is 1 over R, our value of x is, and our value of c is right there. So that is why we say that for us to get the y-intercept, we plot a graph of y, which is 1 over R, against x, which is 1 over L. And this is the graph we plotted. Our value of c is the y-intercept, which is negative 1 over R, which is right there. And it is from here that we are able to get our internal resistance. Our value of x is 1 over L, which so happens to be the x-axis. And our value of y is 1 over capital R, which is right there. So it means that when you are tabulating your results, you make sure that in your table of results you include values of 1 over capital R over 1 over L. And that is how we get the internal resistance of a cell using a potentiometer. The principle of a slide wire potentiometer. Now this is a potentiometer circuit diagram. It definitely has a driver cell. This driver cell is connected to a circuit we are calling the primary circuit, and of course the primary circuit has got this slide wire connected to it, this uniform slide wire, and of course this uniform slide wire below here is what we are calling the secondary circuit, and of course this primary circuit is connected to the secondary circuit, which is always down here. Now a potentiometer consists of a uniform slide wire, and this slide wire can be of any length. It can be 1 meter long, it can be more than 1 meter long. This slide wire is connected in series with a driver cell, and this driver cell is responsible for ensuring that there is a constant flow of current through this slide wire. Now since the wire has got a uniform cross-sectional area, it means its resistance also is going to be uniform. And now since it's going to have a uniform resistance all through, by uniform resistance I mean it is having a uniform resistance per centimeter, it means that this driver cell which is connected to this wire is also going to deliver a uniform potential difference per centimeter, which we are calling PD per unit length. So it means that every time you move, let's say 1 centimeter, the potential difference will, let's say, maybe 1 volt. If I'm to move 2 centimeters, it means the potential difference across that portion of the 2 centimeter wire will be 2 volts. If I move 3 centimeters, it means that the potential difference across that portion of the wire will be 3 volts. So what does this mean? It means that the potential difference that is across this wire is uniformly distributed all throughout the wire. And so because the wire is uniform and it is having a uniform resistance per centimeter, it means that this driver cell is also going to impose a uniform PD per centimeter along that wire. Now how a potentiometer works is that an unknown potential difference is connected across the secondary circuit, and when this unknown potential difference is connected across the secondary circuit, this sliding jockey is tapped along the slide wire until a point whereby this galvanometer shows no deflection. When that point is arrived at or is achieved, when this galvanometer shows no deflection, it means that the potential difference across that portion of the balance length is equivalent to the potential difference across the unknown potential difference that has been connected in the secondary circuit. Now, since the potential difference across the balance length is the same as that, it's the same as the potential difference across the components in the secondary circuit at balance, and we know that the potential difference is directly proportional to the length. So it means that for us to be able to get that potential difference, the value, we are simply going to get the potential difference per unit length, or the PD per unit length, which we are denoting as K, times the balance length. So it means that if the potential difference here is, the PD per unit length here is 1 volt per centimeter, meaning that for every 1 centimeter, the potential difference is 1 volt across that 1 centimeter portion of the wire. And we find out that the balance length after moving this jockey is less than 10 centimeters. It would mean that for us to be able to get the potential difference across the balance length will be 1 volt per centimeter, multiply that by the balance length, which is 10 centimeters, and we'll be able to get the voltage, which is 10 volts. And those 10 volts, which is the potential difference across the portion of the balance length, will be the same, or will be the potential difference across the unknown potential difference that has been connected in the secondary circuit. Now, for those of you who might be wanting to take notes, let me repeat the principle of a slide wire potentiometer briefly. Now, a potentiometer consists of a uniform slide wire, and this slide wire can be of any length. It could be 1 meter, it could be more than that. Now this potentiometer is connected in series with a driver cell which maintains a steady current through the wire. Since the wire is uniform, it has a constant resistance per centimeter. This therefore means that the driver cell applies a constant PD per centimeter across the length of the wire. Now since the potential difference across the length of the wire is directly proportional to the length, it means that we can easily get the potential difference across the portion of the wire from this expression, V is equal to KL, where the value of K simply stands for the PD per unit length of that wire. In this case, if this wire is in centimeters, it means this is the PD per centimeter of the wire. So in practice, the unknown potential difference is balanced against the slide wire by placing a jockey along different parts of the slide wire until the galvanometer shows no deflection. In order to obtain a balance point, this unknown PD that we are connecting in the secondary circuit must be connected in opposition to the driver cell. By this I mean that the positive terminal here should be connected to the positive terminal right there. This is positive, that is positive, the two connect at the point A. And of course the EMF of the driver cell has to be greater than the EMF in the secondary circuit for you to be able to obtain a balance point. And that's the operating principle of a slide wire potentiometer. How to use a potentiometer to compare resistances. Now the resistances we are trying to compare are these two resistances. We have RS, which we are whose resistance we know. It's a standard resistor whose resistance we know. Of course, when I call it a standard resistor, it means that its resistance is known. Then we have R naught. We do not know the resistance of this, but now we are going to use this potentiometer setup to try to compare these two resistances and hopefully be able to even get the resistor that we do not know. Now in this setup, of course, our normal setup of the apparatus is like that. The driver cell, we have a variable resistor there, P1, then we have the EMF, source of EMF in the secondary circuit. We have these two resistances. But now here the thing is, there are two major steps we are going to be taking. The first step is that we are going to balance this resistor, whose resistance we know, against this slide wire. So it means that part A is going to be connected to part C, and then this part of the jockey, which we shall call J, is connected to part D, and then we will be able to get the balance length. Now afterwards, we shall shift this wire and connect it to part D. This part A will be connected to part D, and then this wire will be moved to part E, and then we'll be able to balance the potential difference across this resistor whose EMF is unknown, whose resistance is unknown, against the slide wire. So the first step, first of all, is to make the connections A to C, and of course this to that. The galvanometer is connected to part D. If I may redraw this diagram, this is how it would look like. We connect part A to part C, and the galvanometer is connected to part D. We tap the jockey of the galvanometer across the slide wire AB up to a point where the galvanometer shows no deflection. When that point is achieved where the galvanometer shows no deflection, we will be able to measure off the balance length, and then we measure it and record it. Since the balance length we will be getting will be for a resistor RS, a standard resistor, it means we shall call the balance length also LS. And of course at balance, the potential difference across the slide wire, which so happens to be the PD per unit length, which is K, times the balance length LS, should be equal to the PD across RS, which is the current going through the RS, which is I, times the resistance, which is RS. And that's the expression, that at balance, that IRS, this is the PD across the resistor, is equal to the PD across the balance length. That is our first expression. So after that, we'll go ahead and shift our connections. This wire SC will be shifted, and now it will be put from A is connected to D. Then this galvanometer is shifted from connecting to this portion to that portion, so that now we balance the potential difference across this resistance, whose resistance we do not know, against that wire AB. If I may redraw this diagram, this is how it would look like. That we shifted this wire and we put it there, connected A to D, and then the galvanometer that was here is connected to point E, so that this resistor, whose resistance we do not know, the potential difference across it is balanced against the slide wire. And of course we move our slide jockey along that wire. We tap it on different portions along that wire up to a point whereby the galvanometer shows no deflection. When that point is achieved where the galvanometer shows no deflection, the potential difference across that balance length is going to be equal to the potential difference across that resistor R naught. And of course the potential difference across the balance length is given by K, which is the PD per unit length. Multiply that by the balance length, which we shall call L naught, is equal to the potential difference across this resistor, whose resistance we do not know, which so happens to be capital I, which is the current going through that resistor, times the resistance of that resistor R naught. And that is the expression, that I times R naught, this is the PD across the resistor, is going to be equal to the PD across the balance length. Now we have two expressions here. Now that we have this expression and that expression, we go ahead and divide them to be able to compare the resistances. So when we divide expression 1, which is so happens to be that, by expression 2, of course this I and that I will go, this value of K and that value of K will go, we remain with Rs over R naught is equal to the balance length, Ls over L naught. And from this expression, we are able to get to compare the resistances using the potentiometer. And that is how we compare resistances using a potentiometer. How to measure current that is going through a resistor using a potentiometer. Now this is the setup of the circuit that we will be using. Our intention is to find the amount of current that is flowing through this resistor, Rs. So of course, our primary circuit is as usual. We have a driver cell and a variable resistor P1. Then this is our slide wire AB, and this is connected to our secondary circuit. Our secondary circuit is having an EMF, a standard cell whose EMF is known. That's why we are calling it ES. And we have this other circuit down here that is containing a variable resistor, a cell, and a resistor Rs, and we need to find out the amount of current that is flowing through this Rs. Of course, we have switch S here, which can either be connected to position 1 or position 2. When we connect this switch S to position 1, it means that we have killed this lower part of the circuit. When we connect this S to position 1. And so it means that the secondary circuit will be only that. That will be the circuit. And now, of course, when we connect S to position 2, it means that this portion is killed. It's redundant. It's no longer actively involved in the circuit. And so it means that our AJ will be balanced against what is here. And now here, for us to be able to find the amount of current going through Rs, we need to first find the PD per unit length. So the two major steps here is first of all to find the PD per unit length of AB. That is the same as saying we first calibrate this potentiometer. Then after finding the PD per unit length of AB, then we'll go ahead and find the amount of current going through this resistor Rs by balancing this Rs against the slide wire. So to begin off with our experiment, first of all, like I had said earlier, we first calibrate the potentiometer wire AB to be able to know the PD per unit length. So we do that by first of all placing S in position 1. We place S in position while when K is open. Of course, when K is open, it means that the protective resistor is within the circuit. So when S is in position 1 and K is open, we move this jockey along the slide wire AB, and then we get an approximate balance point. And that approximate balance point is got when the galvanometer shows no deflection. So after that, we close K. When we close K, it means that now we've bypassed this protective resistor by closing switch K. And then we go ahead and find the accurate balance point. And when we get the accurate balance point, we go ahead and find the corresponding accurate balance length that is corresponding to that accurate balance point. And of course, we know that at balance, the potential difference across the balance length is equal to the potential difference across, in this case, since S is connected to 1, it's going to be equal to the potential difference across ES. And this will be it. That ES, which is the PD, is going to be K, which is the PD per unit length times the balance length we got. And when we make K the subject of the formula, K is going to be ES over L. K, therefore, in this case, is the PD per unit length. Now that we've obtained the PD per unit length, we go ahead and find now, we balance the potential difference across this resistor, the standard resistor, whose resistance we know. We balance it up against the slide wire. So how do we do this? We do this by connecting S to position 2. Of course, when you connect S to position 2, while K is open, we go ahead and tap this jockey along the balance length, tap this jockey along the slide wire until we obtain a point where the balance point shows no deflection. And after obtaining the point where the balance point shows no deflection, we will have obtained an approximate balance length. So we go ahead and find the accurate balance length by closing switch K. When you close switch K while S is still connected to position 2, we still move this jockey along the slide wire AB until we get the accurate balance point. When we get the accurate balance point, we go ahead and measure the accurate balance length corresponding to that accurate balance point, and we go ahead and record it. Of course, the potential difference across AJ will be equal to the potential difference across this standard resistor. And in this case, the potential difference across the resistor, standard resistor, which is I times R, I being the current going through the resistor, times the resistance RS, the resistance of the standard resistor, is going to be equal to the potential difference across the portion of that wire of the balance length, which so happens to be the PD per unit length times the balance length L. And this is our equation 2. So since we already got the expression for the value of K, which is the PD per unit length, which we got in our equation 1, which is right here, we go ahead and substitute for this value of K in this. So it means that just like we did here, IA is equal to RS times KL, this value of K is substituted. We substitute for the value of K from our equation 1, and we get an expression. We make IA the subject of the formula, and this is the expression we get. So we are able to find the amount of current flowing through that standard resistor from this expression, this being the EMF of the standard cell, the balance length, the respective balance length we've been getting in our experiment, then the resistance of the standard resistor. And that is how we measure current flowing through a resistor using a potentiometer. How to calibrate an ammeter using a potentiometer. Our two major huge steps are, first of all, to find the PD per unit length of this wire, that is calibrating it. We are going to connect S to position 1 and we balance it against the AB. Then afterwards we connect S to position 2 and we balance this lower portion of the circuit against the wire AB, and then we are able to get the calibration curve of the ammeter. So we begin our experiment this way. Of course, first of all, we will establish our experiment and connect it like we have seen right there. After connecting our circuit diagram like that, we are going to put S to position 1 with K open. When we put S to position 1 with K open, we slide this jockey along AB. When we slide this jockey along AB, we will get an approximate balance point. And that approximate balance point is gotten when the galvanometer shows no deflection. So afterwards, we will bypass this protective resistor by closing switch K. And when we close switch K, while this S is still on position 1, we will still tap our jockey along the slide wire AB up to a point where the galvanometer shows no deflection, and then the balance length is obtained and we're able to get our accurate balance point. And when we get our accurate balance point, when S is on position 1 and ES, this is a standard cell, it means that we are able to get the PD per unit length of that wire AB, because the potential difference across that balance length will be equal to the potential difference across our standard cell. So we'll go ahead and say that the PD across the balance length that we get is equal to the EMF of this cell, and that's how we're able to get our PD per unit length. And that is our first expression, that the ES, which is the PD across the standard cell, is equal to the PD per unit length K times LS. We have called that balance length LS. So from there we go ahead and connect S to position 2. When we connect S to position 2 with K open, it means that we are trying to balance the resistance of this standard resistor across the wire AB, this slide wire. So with S on position 2 while K is open, we'll go ahead and tap the jockey along the slide wire AB. Then we'll get an approximate balance length. Then after getting the approximate balance length, which is got when the galvanometer is not showing any deflection, we'll go ahead and close switch K so that we bypass the protective resistor. When we close switch K, we continue to tap this jockey along this wire AB, and then we will be able to get our accurate balance point. And when we get the accurate balance point, it means that the potential difference across this RS is equal to the potential difference across the balance point we will have gotten. So that's our expression, that the IA, which is current going through that resistor, times RS is equal to KL. When we substitute for this value of K, the PD per unit length, which is ES over LS, which we got in our first equation, we're able to come up with as expression when we make IA the subject of the formula. And so we're able to get the actual amount of current that is flowing through this resistor, RS. So when we get the amount of current that is flowing through this resistor RS, what we do here is, now we continue and carry out this experiment again. So it means that we will keep adjusting this rheostat or this variable resistance so that we get new values of current I. When we get new values of I here, we repeat the whole experiment and we keep getting different values of IA. So as you repeat the experiment, you adjust this rheostat to get new values of A, or new values of current, or new readings on the current. Then we carry out the experiment and we're able to get the amount of current that is actually going through the resistor, the standard resistance. Using this expression, we tabulate our results. By tabulating our results, I mean that we are repeating the experiment with different values of the ammeter reading, with different readings on the ammeter reading. When we do so, we are getting corresponding values of, we record the corresponding balance lengths, and when after recording the corresponding values of balance lengths, we are able to get the actual current that is going through the standard resistor using this expression right here. So after tabulating our results, we draw a graph of IA against I. And the graph of IA against I gives us the calibration curve for the ammeter. And that's how we calibrate an ammeter using a potentiometer. How to calibrate a potentiometer using a voltmeter. This is Kisembo Academy. So in today's video, we are going to look at how we calibrate a voltmeter using a potentiometer. This is the voltmeter that we seek to calibrate. To start off with the experiment, definitely this is how our setup is going to look like. Our potentiometer circuit will be connected as usual with a variable resistor in the primary circuit. The primary circuit has a driver cell, a slide wire AB, which slide wire is connected to a secondary circuit that is having a cell that is standard, that is a standard cell. And of course, by standard cell, I mean that the EMF of this cell is known. We have this other portion of the circuit having a variable resistor P2 connected to a standard resistor. By standard resistor, I mean that the resistance of this resistor is known, and we are having a voltmeter connected across. We have switch S that can either be connected to position 1 or position 2, and this is connected to a galvanometer. And of course, to protect this galvanometer from excess current, we connect this galvanometer in series with a protective resistor P, which can be bypassed by simply closing this switch K whenever necessary. So the first thing here is we are going to first standardize the cell. And afterwards, we'll go ahead and find the potential difference across this other portion of the circuit so that we're able to get the values we want that will enable us to get the calibration curve of the voltmeter. So to begin the experiment, first, we are going to place switch S in position 1. We are going to place S in position 1 with switch K open, and then we shall slide this potentiometer wire across the slide wire until we reach a point whereby the galvanometer shows no deflection. When we attain the point whereby the galvanometer shows no deflection, we will then close this switch case so that we bypass this protective resistor. We bypass it, and then we get the actual balance point while S is still at position 1. And of course, after doing that, when you get the balance point, when K is closed and when S is on position 1, we know that the potential difference across that balance length we will have got will be equivalent or equal to the potential difference across this standard cell. And by that will give us our first equation. And the first equation in this case is that the ES, which so happens to be that, the PD across that cell, which so happens to be the EMF of that standard cell, is going to be equal to it's going to be equal to the potential difference across the portion of that wire length, which so happens to be the PD per unit length of that wire. Multiply that by the balance length we got, LS, and definitely K here is the PD per unit length. So this first portion, this first equation, gives us the value of K, the PD per unit length. So this value of K we've got in this expression is supposed to give us, we're supposed to be able to substitute it in our next expression. So we continue with the experiment. We now go ahead and connect switch S to position 2. We connect switch S to position 2 while K is first open. You know that when K is open, it means that the protective resistor is in series with the galvanometer. So when S is at position 2 while P is, when switch K is open, we will slide this potentiometer wire, this sliding jockey, along the slide wire AB up to a point whereby the galvanometer shows no deflection. When that balance length we will have got at that point will be just the approximate balance length. So we get the accurate balance length by closing switch K. When we close switch K, we are bypassing the protective resistor, so the current coming in will bypass this resistor. And so it means that when switch K is now closed, when S is still at 2, we will again tap this jockey along the slide wire AB until we attain the accurate balance point. And definitely the potential difference we will have gotten at the balance length will be equal to the potential difference across this standard resistor S. And so we'll develop another expression. And that expression will be VA, which so happens to be the potential difference across that standard resistor S, is going to be the PD per unit length times the balance length we will have got L. And of course, this value of K, which is the PD per unit length, is what we substituted in our first equation. This value of K, when we make K the subject of the formula, K becomes ES over LS. So this, we substitute that in the second equation. So in this second equation, the value of K is what we put here, and it is what we put right there. VA is right there, then L. Then of course, this is the expression for the PD across L. So we repeat this experiment for different readings of the voltmeter. By voltmeter, I'm talking about this voltmeter. We get different readings for this voltmeter. We repeat this experiment. Of course, we get different readings for this voltmeter by adjusting or by regulating this P2. So the experiment is repeated for different readings of the voltmeter so that we are able to get different values of VA. So we tabulate our results, and in our results we shall be getting the different readings of the voltmeter V, and then we have a column for VA. We have also a column for the corresponding balance lengths that are corresponding to this VA we are getting. And then when we plot a graph of VA against V, we are able to get the calibration curve for the voltmeter.
This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.